Laplace transforms are a great way to solve differential equations. Basically, you can end up solving a differential equations without actually doing any calculus, so to speak, to do it. You end up turning it into an algebra problem. Let's take a look at a very easy one that we've kind of solved in the past. Let's say we had something like y double prime plus y equals, who knows, 0. And we know that y of 0 is 0 and y prime of 0 is equal to 1. Now, here's one of the big catches with having to use using Laplace transforms to solve differential equations. You have to know something about the original function at 0 up to the n minus 1 derivative. As we saw when we took the Laplace transform of a derivative, we make it all the way up to the n minus 1 derivative, and we need to know those values at 0. All right, we've solved this in the past, and hopefully you can see that your characteristic, I'm just going to squeeze this down here real quick. Our characteristic equation would be m squared plus 1, so we get plus or minus I. So we would get our y is equal to c1 cosine x plus c2 sine x. And then we would go and we would use our initial conditions to figure out what our constants are, our c1 and c2. So let's see how this works out with Laplace transforms. So we take the Laplace transform of the entire equation. So the Laplace transform of y double prime, Laplace transform of y. And don't forget, you got to do the Laplace transform of the other side. So we solve the Laplace transform of derivative. This gives me s squared Laplace transform of y minus s times y of 0 minus y prime of 0. Plus, I don't know what the Laplace transform of y is, and the Laplace transform of 0 is 0. Okay, now notice we have a couple of unknowns. We don't know what the Laplace transform of y is, because remember, we're trying to solve for y itself. So our goal now is to solve for the Laplace transform of y and then do the inverse Laplace transform. Well, from here we know y of 0 is 0, so that piece goes away. And we know y prime of 0 is 1, so that turns into 1. So we get s squared Laplace transform of y minus 1 plus the Laplace transform of y is equal to 0. Now we're going to solve for this Laplace transform of y, so let's move the number to the other side. And we can factor out the Laplace transform of y out of the two terms, and we get s squared plus 1 is equal to 1. All right, I just factored this out of these two terms. So if we solve for the Laplace transform of y, we get 1 over s squared plus 1. So to come up with our answer, we would do the inverse Laplace transform. So our answer is going to be s squared plus 1. Now, it's this step that's generally the most work for these problems because, as we've seen in the past, the inverse Laplace transform is not necessarily easy to do. This one is, just by definition, that is just the sine of x. So notice we didn't really do any calculus here. We used a few properties of our Laplace transform, and we used a table to get back out. So it's a very, very nice, clean way to solve a differential equation. Now, most of the time, when you use a Laplace transform to solve a differential equation, you're turning it into an algebra equation, solving that algebra equation and using the inverse Laplace transform to get back. Now, that doesn't mean that every time you do the Laplace transform, it turns it into an algebra equation. Sometimes you still end up with a differential equation, but one that's generally easier to solve. Let's take a look at, let's do ty double prime minus y prime is equal to t squared. And let's say we know y of 0 is 0. So this is a actually much harder example of what can happen when we do Laplace transform to solve differential equations. All right, again, let's take the Laplace transform of everything. Ty double prime minus Laplace transform of y prime equals the Laplace transform of t squared. Okay, now we got to use a couple of our properties. Remember, if we multiply by t in the t world, in the Laplace transform, that's a derivative in the s world, and it's the -1 to that power. So we got to take the derivative of the Laplace transform of y double prime minus, let's see, the Laplace transform of y prime, that's going to be s times the Laplace transform of y minus y of 0. Oop, wrong bracket. Okay, so this is the Laplace transform of y prime. And of course, on the other side, we need to do the Laplace transform of t squared. So remember, our Laplace transform of t to the n is n factorial over s to the n plus 1. So our n is 2, so it's 2 factorial over s cubed. All right, so got a lot more work to do here. Let's go ahead and do the Laplace transform of y double prime, because we know that's going to be s squared Laplace transform of y minus s times y of 0 minus, the s counts down, so y prime of 0. I'm going to go ahead and distribute this as minus s Laplace transform of y plus y of 0, 2 over s cubed. All right, got a bit of a mess going on here, but let's see what pieces we have. We know y of 0 is 0, so that goes away. Notice here, generally we need up to the n minus 1 derivative, so we should have known something about y prime. This is a special case when we actually did need to know it, because here in a second we're going to be taking the derivative of this. Well, y prime at 0, that's just a number, and of course the derivative of that is, well, 0. So all we got to do is take the derivative of this piece. So here we got to do the product rule, so that's 2s Laplace transform of y plus s squared times the derivative of the Laplace transform of y. Well, that's pretty interesting, because now we are going to have a differential equation in the Laplace transform of y. We're going to think about that kind of as our variable. So over here we have minus s Laplace transform of y. Again, we know y of 0 is 0, so we have 2 over s cubed. All right, let's go ahead and distribute here and see if we can clean up a little bit. 2s Laplace transform of y minus s squared Laplace transform prime of y minus s Laplace transform of y, 2 over s cubed. All right, scary looking, but look here. Let's see, we can combine some like terms. I'm going to write this in descending order as our derivatives. So we get negative s squared L prime of y minus 3s Laplace transform of y equals 2 over s cubed. Now remember that derivative, way back over here, is a derivative with respect to s. So you can think about this as s is our independent variable, and the Laplace transform of y is our dependent variable. Now I'm going to do this really quick, but notice if I change the variables here to our normal variables, and I said negative x squared y prime minus 3xy is equal to 2 over x cubed. I just changed up the letters a little bit, so it's what we're used to saying. This is actually a first order linear differential equation. So the first thing we'd want to do is get the derivative alone. So we divide through by the negative s squared. That gives me 3 over s Laplace transform of y equals negative 2 over s to the 5th. Okay, so since it's first order linear, we need to use an integrating factor. And remember, your integrating factor is e to the integral of whatever's in front of the non-derivative term, ds. So we've done these a lot before. This ends up just being s cubed. So we multiply the left-hand side by this integrating factor and integrate. We always get the integrating factor times the dependent variable. On the other side, we need to multiply and integrate. So this is s cubed Laplace transform of y equals, I'm just going to pull the negative 2 s to the negative 2 ds. So this is s cubed Laplace transform of y is equal to, we integrate that, that's 2 over s plus c. So to finish solving for the Laplace transform of y, we just divide by s cubed. So this is 2 over s to the 4th plus c over s cubed. Now notice we do end up with an arbitrary constant here, and kind of to be expected because this was a second order differential equation and we only had one constant, so we should have one arbitrary constant left. So to figure out what y is, all we need to do is the inverse Laplace transform of both sides. So we got to figure out what the inverse Laplace transform of 2 over s to the fourth, inverse Laplace transform of c over s cubed. All right, kind of out of room here, so let's go back over this way. So let's pull out our constants. So this is 2 inverse Laplace transform of 1 over s to the fourth plus c inverse Laplace transform of 1 over s cubed. Okay, so for each one of these, this is s to the fourth, so we need 3 factorial on the top. So 3 factorial would be 6. We need a 6 out front. Here we need a 2 factorial on the top, so if I change that to a 2 and put a 2 out front, so we get y is equal to 1/3. This ends up being t cubed plus c over 2, and that is t squared. Okay, so there you go. There is the solution to our differential equation. So every time that you do the Laplace transform to solve a differential equation, you don't always end up with an algebra problem. Sometimes you end up with a lower degree differential equation to solve. Looks scary when you got all these Laplace transforms floating around, but remember that's just the variable that you're trying to solve for, so you can do the inverse Laplace transform.